while people are coming in.
Sure.
So just for the audience, as a general rules of thumbs for handling questions, what we suggest would be, if you have questions during the presentation, please write them in the chat and I'll try to interrupt if there's something quick that, like clarification basically of what is being said. And for more discussion type of questions, I would ask that you keep those for the Q&A session at the end. Then you can kind of open up your camera and ask directly. And so with that being said, like, it's my pleasure to introduce today's speaker, which is Professor Sanjeev Goyal, who is a professor of economics at the University of Cambridge, is a fellow of the British Academy and a fellow of the Econometric Society. And Professor Goyal was also the founding director of the Cambridge Inet Institute, who I should say is also organizing a very nice webinar around topics of network economics. So for those of you who are interested in those, I invite you to check that webinar as well. And let me say that Professor Goyal is a pioneer and leading international scholar in the study of social and economic networks, with foundational work on network formation, learning in networks, and network game theory. And for those of you who are maybe like new to these topics, you can check his beautiful introduction of the topic in his book, Connection: An Introduction to Economics of Networks. And with that said, today Professor Goyal is going to talk about his recent work on connectors and influencer. So with that, Professor, the floor is yours. And thank you again for agreeing to participate in this seminar.
Thank you, Francesca. I hope you can see the slide and you can hear me. Sorry, can you hear me?
Yes, yes, we can hear you.
And you can see the slide?
Yes.
Okay, just to be sure, yeah. Okay, well, thanks very much for inviting me, and very nice to see Professor Dassar, and I should say that at the outset that this is joint work with Singju Choi from Seoul National University and Fred Mosson, who is now at a business school in Lyon in France. And it's part, the paper I'll present today is part of a larger research program that we have, which is sort of really developing a platform to carry out large-scale experiments on networks. And by large scale, I mean, so these are lab experiments, and they are, they are in continuous time, and they could have, we've had 100 subject experiments, but the platform, the software is supposed to actually, we're hoping it can work very well, even with a larger number of subjects. So, without further ado, let me so this is, as I said, this is part of, this paper is part of this larger project, but I will now, for the remainder of this talk, just talk about this particular experiment. Okay, so this is an experiment on a network formation game. And let me say a few words about the larger motivation behind this work. So one strand of work in economics of networks deals with the formation of networks. There is, of course, probably a larger body of work dealing with behavior in networks. And there is also, of course, work that combines formation and activity in networks. And so this paper that I'll talk about today is in that strand. It's going to have some activity in networks. In addition, there will be linking, so network formation. So economic theory has, there's been quite a lot of interest over the past 25 years or so in thinking about network formation problems. This research has helped us understand equilibrium networks, efficient networks, and the relationship between the two, highlighted tension between individual incentives and collectively desirable outcomes. And two challenges in this field are that often network gains have multiple equilibria, and often it's the case that the efficient networks are unequal. So a classical example of an efficient network that's unequal is a hub-spoke network, which is typically efficient, but typically unequal, okay, with the hub often earning much more than the spokes. And so there's always been some uneasiness about whether these types of networks are going to arise, because people may not be able to coordinate on these efficient networks, even if they are equilibria, and also because apart from the coordination problem, there is the unfairness problem. And so people may not want to get there. Even if they were getting there, they may want to sabotage it. Okay. So what we are going to be doing in this paper is to essentially take a very, very simple, very natural type of a model, which has very clear predictions, equilibrium and efficiency predictions. And we are going to run an experiment. And as I said, the distinctive feature of this experiment is that it's going to be large scale with 100 subjects. And it's going to be in continuous time, which means that people can make choices at any time they like. They don't have to synchronize with others. Okay, so and because it's in continuous time, they can make many decisions. Okay, so they can learn in principle. Okay, a lot more. The high-level takeaway from this experiment is going to be that subjects are going to choose equilibrium networks, which in the set of equilibrium networks will be efficient, and we will see that when you scale up, there are very clear and powerful effects when you scale up the group, and some of those effects are refine the theory and lead us to think about decision rules that people are using in these complex, evolving network environments. So that's the high-level sort of summary of what I'll be doing. So let me to put things a bit in perspective, let me say a few words about the literature. Some of you, I'm sure, are very well informed about this economics literature, but there have been experimental tests of theoretical network formation models, and typically these experiments have rejected the predictions of the theoretical model. So I'm going to talk about a theoretical model, and I'm going to be much more precise in a moment, but let me just highlight that this is a high-level sort of takeaway from the existing experiments. Subjects do not create hub-spoke type networks, and to get hub-spoke-like networks, you have to incorporate asymmetries, or you have to somehow modify the payoffs to get those sorts of structures. Okay, so what we're going to do is we're going to take a model that has been previously tested in the lab, and we are going to actually find rather different results. We are going to find specialization. We are going to get hub-spoke-like networks. And even when the groups are small, we are going to get that. So this has been a feature of existing work. Typically, you have 4 to 8 to 12 subjects. And we're going to also have 4 and 8 subjects. groups, and we will nevertheless get hub-spoke-like networks. So our understanding is that somehow the confirmation of the theory is due to this possibility of asynchronous and continuous time activity in this experiment. Let me just also, by way of putting things in locating our work in the literature, also for some of you, it might be interesting to read some of these papers by Dan Friedman and Brian Oprea and their co-authors. There's now a strand of research which looks at continuous time games. What we are bringing to this literature is that we are looking at these papers are looking at very small number, small games with a few subjects, whereas our interest is in introducing large-scale network environments. And so we've had to introduce a number of novel features in our platform, which allows us to visualize the network in real time and also allow interactive tools for activity, asynchronous activity in continuous time. The paper, which is available online, goes into a lot more detail on the platform. I should probably also add at this point that a lot of the novelty here is due to Fred Mosson, who has a very interesting background in computer science and artificial intelligence. So a lot of what is novel in this really we owe to him. So by way of background, this is it's going to be a paper that tests the model, which I wrote with Andrea Gagliotti, and it's a paper with the title "The Law of the Few." And the Law of the Few is the title of a chapter in a book by Malcolm Gladwell, The Tipping Point. And many of you, I'm sure, have read this book. But the law of the few is this idea that in large social groups, a small subset of people actually acquire information, and the rest of the population acquires very little information on its own, simply talks to this small set to get all the information they need. So that's the sort of idea that we want to take. There are a number of papers, which have this, which have looked at different empirical settings and have identified this law of the few property. So in this paper that Andrea and I wrote, what we did was we tried to model a setting where people have information or something of value that others can, and people can invest in acquiring information. But they can also invest in forming links with others and acquiring the information that other people have acquired. Okay, so that's the basic, very simple setting. And when I form a link, let's say with Francesca, I get access to the information she has bought herself or she has acquired. Okay, so that's, and we showed in this paper that when you write down the game and when you solve for the equilibrium of this game, then it has this law of the few property. Okay, and in particular, when the number of players gets large, the fraction of players who are active in buying information becomes negligible, and everybody else is passive and just links with this negligible group of people who buy all the information. Okay, so that's a theorem in the paper, and let me now write out the model and develop the result very briefly. Okay, we're going to test this model essentially in the lab. So this is a game, an n-player game. It's a one-shot game, and it has so there are two actions people take. They acquire information, which is given by xi, and they form links with other players, which is a vector gi. And the cost of effort, this is continuous effort, is C. So if you buy xi, the cost is CXI. And linking cost is a fixed cost per link. So if I form 10 links, the total cost is 10K. So with that background, I can now walk you through this payoff. So the payoff is X. Players are choosing Xi, Gi. So the vector of activity choices and linking choices is denoted by X comma G. And so given a profile XG, the payoff is f of this function f, which, how much information I bought, the information others have bought, these are my neighbors, and then the neighbors of my neighbors, okay? And we're going to have this idea that A is a number between 0 and 1, so there is some decay in getting information from far off. So this is the very simple model of payoffs. And then since I'm buying xi, it costs me C times xi. And if I form eta I links, then it costs me K times eta I. Okay, so that's the payoff. We are going to assume also that f is an increasing and strictly concave function, and there exists a number y hat such that the marginal returns at y hat, f prime of y hat, is exactly equal to C, the marginal cost of effort. Okay, so this assumption is going to be very helpful. Notice that if I were on my own, then I would just choose y hat. That would be my optimal, action. And so what's the cost of doing y hat? It's simply y hat times C. Okay, so if we got to keep that in mind, notice that if I were doing y hat, would you want to link with me? Well, you would want to link with me only if the cost of linking with me, K, was smaller than y hat of C. Because if it were larger than y hat of C, then there would be no point in you linking with me. You would be able to buy this information on your own, cheaper. Okay, so a key condition for anything interesting to happen in this model is that K, the cost of linking, should be smaller than the maximum information anyone's going to buy personally y hat. So K has to be smaller than C times y hat. Okay, so we're going to be interested primarily in that situation. And in fact, in the paper, we will be looking at K pretty close to y hat times C because we want to keep the network sparse. So, so here's a theorem in this model. There exists some high enough K hat close to C y hat such that for all costs of linking K between K hat and C y hat, the equilibrium is a periphery sponsored star. As the name suggests, it's a star network, hub-spoke network, where the periphery creates the links with the center. The center forms no links at all. But the center, of course, does, in the pure influencer equilibrium, the center invests y hat, everybody else invests 0. And in the pure connector equilibrium, which exists under certain circumstances, the hub invests 0 and everybody else invests some positive amount. Okay, so there are two equilibria. So here's a picture. On the left, I have the pure influencer equilibrium where, let's say, y hat is equal to 10. Everybody else does 0 effort and forms a link with the center. And the pure connector equilibrium is one where everybody connects with the center because everybody else is connected with the center. So this should also make you wonder how information flows. And as you could probably infer, I can form a link with you, but the information flows both ways. So in these pictures, the arrows are indicating who forms the links. So these are both periphery sponsored star networks. But on the other hand, on the left, the information is flowing from the center to the periphery. whereas on the right, the pure connector equilibrium, information is flowing from the periphery to the center and then to the periphery. Okay. So let me pause and just make sure that people are. I'm not seeing the chats. I don't know whether there are any questions, but if there are, this is a good time to ask me if there are any. So this is the basic theory. I won't be discussing the proof of this result. But this is the baseline theorem that I will be taking to the lab. Okay, so we will be asking, for instance, whether subjects do play these type of equilibria, or do they, do they cycle around? Are the networks sparse? And how quickly do subjects get to it? Which of the two equilibria do subjects pick? Okay, so those are the kinds of questions we are going to be addressing.
I don't see any question right now in the chat, but I actually have one quick question, if I can. So I was wondering, this pure connector outcome that can only happen when this parameter is greater than 0, right? If A is very small, then yes. I guess that would not happen because you need this two-hop thing for it to make sense. Okay, perfect.
And I have a question. Is the solution continuous in these parameters which define the underlying gain, like the cost of connections and so on? If you make small perturbations in those values, are there big sort of variations in the outcome?
Yes. So, I guess the answer is a qualified yes, in the sense that, you recall that this K is, it has this, it's a discrete. So what's going to be important is that K lies below C of I hat. As soon as K goes over from slightly under C of I hat to over C of I hat, you will go from a connected to an empty network. So in that sense, it's quite, but we won't be, so as long as you remain, within intervals, I think the problem is fairly well behaved.
Okay, thank you.
Yeah. Okay, so that's what the theory is saying. Let's get into the details of the experiment. Okay, so we're going to be looking at a particular f function, which is plotted for you here. And this is just, for you have to give quantitative numbers to get this thing to work in the lab. And so we picked this, and for y smaller than 14, you have the top row, and if y is greater than 14, you have the bottom row. We're going to assume that xi lies between 0 and 20. Okay. Remember that we're going to have a model where y hat is equal to 9. And indeed, here you can check that y hat is equal to 9. So you should never do more than 9. So setting 20 as, you'll see in a moment when I present the experiment that there could be reasons for doing more than 9. Because we were looking at a static model, but the experiment is going to be in continuous time. So people could be forward-looking, and they might want to invest with a view to earning rewards in the future. Okay, so we will talk about that. Now, K will be set equal to 95. So you see that if C is 11, then 11 times 9 is 99, and it's cheaper to connect. Pay 95 and get information worth 99. Okay, so that's the condition that K is smaller than C times Y hat. A is set equal to 0.5. Okay, so what are the two equilibria? What are the what do they look like here? Well, in the pure influencer case, the hub will choose effort 9, the spokes will choose 0 and form 1 link each. The hub is going to earn 81 and the spokes are going to earn 85. So this is a model in which the equilibrium is fairly egalitarian. There's another equilibrium where the hub does no work at all. Some of the spokes choose 1 and the others choose 0. The hub earns a lot, of course, because the hub is not choosing any effort, is not forming any links. The active spokes earn 74 and the inactive spokes earn 85. Notice the active spokes are choosing effort 1, which costs 11, and that explains the difference in the payoffs. So there is payoff inequality and there's link inequality. Okay, so there's a link inequality in both equilibria, but there's payoff inequality only in the pure connector equilibrium. Okay, so we're going to run an experiment with 4 group sizes, 4, 8, 50, and 100. And we are going to have 4 groups of each size, except for n equal to 100, where we have just 3 groups. Okay, so in all, there are over 1,000 subjects involved. And we are going to have 2 information treatments. I'll come to that in a moment, but there are 4 group sizes, but there are also 2 information treatments. And I'll describe that in a moment. The experiment was run in Linux, which is a lab that is a fantastic resource. And it's a lab based in Valencia in Spain. And when we ran the 100 group experiments, we had to connect 2 labs, the one in Valencia and the one in Castellón, because the capacity in Valencia was only up to 60. So we had an internet connection between the 2 labs, and we had 2 labs concurrently running the experiment. So let me say a few words about this platform. I should say this platform is open. It's an open platform, so any one of you who would like to run experiments, we haven't made it public yet, but if any one of you is interested in running experiments, do drop us a line and we would be happy to share the software we have. So let me talk about, I've talked about large scale and continuous time, but let me talk about some other features of the platform which make it attractive. So here's a first issue, which is to do with visualization. Okay, so networks are, as again, many of you are aware, the way you visualize networks can actually make you see the networks in a very different way. Okay, so here's an example. So this is the network, and I can sort of use a different program to visualize it, and it looks like this. Okay, the same network. So now you can see that the network on the right is in some ways much easier to navigate. Supposing you're trying to figure out how far people are, you can probably see this much more clearly in the second network. You can also see who the well-connected people are. And that may be relevant, in some experiments. Similarly, here's another example, and this is how it looks when I just put nodes and fixed positions, and this is how the network is if I re-visualize it. Okay, so that's one thing we've done, and again, the details are in the paper, but we use a very particular algorithm to visualize networks, which allow us to essentially centralize the very highly connected nodes, and at the same time separate the highly connected nodes to make them more clear. Okay, so the details are described in the paper, but the visualization is in real time, and it uses this algorithm, which is quite a well-known algorithm. The other thing that's important when you're running an experiment like this is how much information of the network are you going to provide. Okay, so for example, you can provide subjects only knowledge of their own neighbors, or you can provide them knowledge of the entire network. And as many of you have written papers on how network knowledge affects behavior. That's going to be important. And of course, if you provide the information on the entire network, it's going to be informationally very demanding for subjects, but it may be easier to make strategic decisions. So that's a trade-off. So here's an example of very low sort of, this is player 8, this is me in yellow, and I'm seeing my 3 neighborhood, okay, in this example on the left. And people outside the 3 neighborhood are put on the right, and I don't really know what the network is. Here's on the other hand, an example of the complete network being shown, okay, to this person. So that's a variation. Another variation that's going to be potentially important is how much information about payoffs do I provide? So I might provide information about your own payoffs. That seems to be necessary to make decisions. But should I provide you information on everybody else's payoffs, or should I provide you information only on your neighbor's payoffs? Now, if you're doing imitation-based decisions, probably that's going to be important. If you're learning about how this game is played, probably it's going to be important if you can see the payoffs of others. So, so again, we can have different variations. Here's an example where I just see my own payoffs on the top of the screen, and I don't see anyone else's payoffs. And here's a screen where I have color-coded everyone's payoffs. Okay, and so you can see everyone's payoffs just very roughly, but through the color of the node. Okay, of course, I could give you the exact payoffs. I could give the number, and that's another treatment we have in another paper. So these are some dimensions of the platform that we can vary. But let me go back now to our experiment. So what we're going to do is we're going to have this particular baseline treatment where I only see my own payoffs. We'll have another treatment where I show you the payoffs of everyone. And I'm going to show you the 3 neighborhood in this experiment. Okay. So with that background, let me just wrap up the description of the experiment. So each group is going to play 6 repetitions of the same game. Each game is played for 6 minutes. And the first round, if you like, is purely trial. And the second round onwards is for payoffs. But the first minute in each round is again trial. Okay. So we're going to use the last 5 rounds, and we will use the last 5 minutes of the last 5 rounds to do the empirical analysis. Okay. So we're going to start with the baseline treatment where you see the local network and you see just your own payoffs. And then I'm going to have another treatment where you see your own payoffs, but you also see the payoffs of everyone else. Okay. So we want to start by looking at the macroscopic features of the data, and then we will look at behavior. So let me show you an animation of a representative animation of the 100 subject experiment. So there are 100 nodes which reflect, the 100 subjects. It's a 6-minute experiment. I'm going to run it fast so that we can get a picture of, the dynamics. So what I'd like you to do is keep in mind that this is happening in more or less as we see it, a bit faster. The representation is, the picture is running faster than in reality. And I would like you to remember the theoretical prediction that you should be getting a hub-spoke network. And I'd like you to remember that the effort should be always less than 9 or maximum 9. And with those few comments, let's see what happens in the experiment. So the size of the nodes reflects the effort level. And I've got green and red because they are the nodes that I want you to think about, because you will see in a moment that they will be the key players in this drama. So green is the current hub, the favorite, working very hard, but starts shading her effort. And then red is still persisting with basically close to 20. And you see by minute 3, people are beginning to abandon green and move to red. And you see as we go into the final lap, green has been more or less completely abandoned, and red is the hub. And red is working very hard to keep being the hub. Okay, so this is, and we don't get literally a hub-spoke network, but we get something which is essentially very close to a hub-spoke network. So that gives you a feel for what happens in this experiment. And so this is, remember, it's a 6-minute experiment. This is just showing you the snapshots to focus your mind on. Already you have player 26, who's become the hub, is putting in effort 20, which she should never be doing. She should never do more than 9. Okay, so this is clearly massive effort, maybe to become the hub and then start shading, which is what she does. She goes down to 3, but 97 is persisting with 20, and very soon people have abandoned player 27 and gone off to 26 and gone off to 97. Okay, so that's a summary, so just to summarize, we have extreme specialization in linking and efforts. Practically, everybody is linked to a central person. That person is putting in lots of effort. Most of the others are putting in 0, and some of them are putting in 1 or 2. We see there's intense competition among a few subjects to become the hub. And finally, we see the pure influencer equilibrium. The highly connected central person is putting in pretty much all the effort. Okay. So, Francesca, how am I doing for time?
Yeah, you have still 20 minutes. So.
Okay. Yeah. Okay. So what we've got here, this is very much an economics way of looking at inequality and specialization. So what I'm doing is I'm plotting the Lorenz curves on the x-axis. I'm looking at I'm looking at the this is for in degrees on the left and efforts on the right. So let's look at the one on efforts, which is a bit easier. So I take the total effort, and then on the x-axis, I look at the 20% lowest effort, and then I look at 80% total effort. Well, who's putting in? What fraction of people are putting in the effort? And you see that as I increase the group size, the Lorenz curves are more or less going down systematically, and then the area between the 45 degrees line and the curve, that's that is that divided by half, by the entire triangle. That's the Gini coefficient. That number is given by this, G on the picture. It goes up as I keep increasing the group size. It keeps growing up. Okay, and so inequality grows with group size. And let's look at effects of group size on efforts. Remember that in equilibrium, people should never put in more than 9. And so here we are seeing that what I've done is I've plotted the most connected person. This is the time series. Okay, what I do is let's say at second 100, I look at the most connected person and I ask how much effort has she put in across the 6 rounds and across the 4 groups. Okay, and then I see that she is roughly putting in around 9 in the small groups. Also at n equal to 8, she's putting in around 8, 9, 10. Okay, which is, remember, very close to the equilibrium prediction of 9. On the other hand, when I look at the group of, let's say, group 100, I see that the most connected person is putting in essentially close to the maximum allowed, which is 20, which she should never be doing in a static game. In a static game, she should never do more than 9. So of course, in a dynamic game, I might take the view, I'm going to become the hub by putting a lot of effort. And then once I've become the hub, I'm going to shade. And hopefully people will respond by playing the pure influencer equilibrium. And then I will make lots of money. Okay, so that could be, a thought that might be driving this. Okay, but it's worth thinking that it's worth keeping in mind that this is only happening in large groups. Okay, it's not happening in the small groups. And I'll come back to whether one can rationalize this sort of investment behavior, thinking about it on a dynamic perspective. Okay, but so what I'd like you to take away from this is very large scale effects on efforts, competition, okay, to be the center. The other side to the story is, are people better off? Okay, what happens to payoffs? Well, remember the equilibrium payoffs were essentially 81, 85 in the pure influencer outcome, right? So the hub was getting 81 and the spokes were getting 85. And that's very close to what you're seeing in n equal to 4. It's also pretty close to what you are seeing for n equal to 8. In fact, the hubs and the spokes are earning something close to 90. And, that's not exactly the equilibrium prediction, but it's very close to it. Things are very different when you look at n equal to 100. So what you see here is, or n equal to 50, what you see here is that the spokes are earning close, a bit higher than 85. They're earning over 100. But the central guys, because they're putting in so much effort, they're actually earning a lot lower than that. Okay, they are actually earning below 50. They should be earning around 80. So in fact, they are putting in too much effort, and the result is they're earning too little. Okay, so that's a summary of the baseline experiment. The very powerful group size effects on effort and on payoffs. But I should say that the specialization in linking and efforts is a feature of all group sizes. Okay. So the question is, why do these two most connected subjects compete so hard? And why is it that they compete so hard, and why do they make so little money? How can we account for this? So here's what we do is our view was that it may be that subjects are not understanding, how they could be doing better. They think they would be doing very well by becoming the hubs, but maybe they don't fully appreciate the passage of time, and they leave it too late. Maybe they compete too much for too long. And that may be because they are not understanding that they are not actually doing as well as the spokes, because it's too complex. So what we do is we show them, everyone, the payoffs of everyone. Okay, so in the baseline, you only saw your own payoffs. Now you will see the payoffs of everyone. Okay, and we are hoping that that would expedite learning and would help them overcome, if you like, this excessive competition problem. So let's see what happens. So again, you will see competition, and you should keep in mind the effort level of the hub and the competitor. So you see Mr. Red, and he's doing a lot of work, not 20, but he's doing a lot of work, and people are linking with him, and there isn't he doesn't go down to a very low level effort, but he's shrinking, he's shading, but people remain connected with him. They don't abandon him because the other folks are probably not putting in huge effort. So what you see here is that red is pretty small because he's putting in rather little effort, but he remains the hub. So the challenges are not aggressive. Okay, so you get something which is pretty close to a hub-spoke network, very highly centralized, but the hub is not actually putting in very large efforts. Okay. So here's snapshots. You see these players are fighting it out, and player 23 has gone down to 9 and goes down to 0 and still remains the center. Okay, so so with the payoff of everyone being shown, we find that the behavior of the key subjects who want to become hub is quite different. Okay, so there's still specialization in linking and efforts. There is hubs emerging. The hub starts with a large effort, but then shades her effort without too much pressure from the challenger, and you get a pure connector outcome because the hub is doing 0 effort, everyone's linking with her, and they're putting in some effort. Okay, so this is very close to a pure connector outcome. So as a result, the hub is going to earn a lot more than the spokes. Okay, so let's look at the treatment effects on efforts. We see that, interestingly, when you look at n equal to 8, for instance, the most connected player is doing around 8, 9, which is what they were doing in the baseline treatment. But the big difference is when I look at n equal to 100, I see that the most connected person is actually doing much less than 9. Okay, remember that in the other baseline treatment, they were doing close to 20 at the start, and even at the end, they were doing 14 or 15. Okay, so you see that here, the most connected person is actually almost doing, around 5, which is not quite the pure connector, which would be 0, but they're doing very, very little effort. Okay, as a result, of course, the mirror image of their effort is the payoffs, and you see that payoffs in the small groups are pretty close to equilibrium payoffs, which were around 85, but the payoffs in the large groups, remember when in the baseline in the large groups, the active, highly connected players were earning much less than the spokes. Here they're earning a lot more because, of course, we are closer to the pure connector equilibrium. Okay. So, so you see that the effects in the small groups, there are no large effects of information provision. There are rather large effects in the large groups. Okay, so that's the main takeaway. So scale interacts with payoff information to create large effects on behavior. So to summarize, the behavior of poorly connected individuals is similar across all treatments. And indeed, one can show formally that they are essentially playing a myopic best response. So they look around at the world and they play, what is optimal in the face of this environment. Their behavior is very well described by that myopic best response. Behavior of highly connected subjects differs in large groups. In the baseline, they put in large efforts and earn low payoffs. In the information treatment, they put in low efforts and earn high payoffs. So we want to understand what's the decision model that can account for this sort of very different behavior. So as I said, the poorly connected spokes, you can essentially, what you do is you look at point T and you look at a myopic best response at T+1, and you compare that to the actual behavior in the lab at T+1, and that's a very good match when you do the poorly connected spokes. But of course, we know that for the highly connected subjects, myopic best response could not possibly be an explanation for behavior because, of course, you would never do more than 9 in a myopic best response, whereas they were doing 15, 16 effort levels, which are well above, which was something that could be rationalized. So surely they can't be doing myopic best response. Maybe they are doing some other decision rules. So what we did was we came up with a decision rule, which has, so we had a decision rule which is described here informally. So what it says is, given some behavior in the past, so you were choosing some effort, your person I, and you're choosing XIT, and I'm person J, I'm choosing XJT, and the two of us are competing. We are highly connected, and we are competing to be the hub. So the decision rule says, well, if we are competing, in other words, if our efforts are close by to each other, they're within some interval, let's call that theta, then we are competing. And if you are doing more effort, then you're going to be choosing some target effort, X bar. And if I'm following you, then I will try and imitate you. Okay, so that's the decision rule. So the two variables are theta, that's the competitive interval, if you like, and my target X. If I were leading in a competition, how high would I go? That's X. So what we find is that when we estimate these parameters from the data, so we can plug in this decision rule and we can estimate the best fitting coefficients for X and theta in the data, we find that there are significant differences when we look across the large payoff and the large baseline treatment. In particular, the estimates on X are much higher for the baseline. Okay, so in other words, when I'm competing with you and I'm ahead of you, I'm choosing a much higher effort in the baseline treatment as compared to in the information treatment. When I'm faced in the information treatment, when I'm ahead of you, I choose a much lower target X. Okay, and that in our mind gives us, some explanation that perhaps, and this is only true when we look at large groups and information variations. It is not true when we look at small groups. So that, I think, gives us a feel for why, how we might sort of think about information provision as affecting a key aspect of the decision variable and probably accounting for differing behavior in the two different experiments. So let me sum up. So what we have done is we've run a 4x2 experiment, 4 different group sizes, 4, 8, 50, and 100, and 2 payoff treatments with just your own information and on payoffs and the information on everyone's payoffs. And the first high-level takeaway is that irrespective of the treatment, we get a network which is very highly specialized in linking and very highly specialized in efforts. So that supports the law of the few result. And we also find interesting effects of the treatments on which equilibrium is picked, whether you pick the pure influencer equilibrium or the pure connector equilibrium. Finally, we find strong dynamics of competition, which are, of course, beyond the static model we were looking at, and they seem to be related to scale and to information. And finally, I didn't do it formally, but a long section in the paper which estimates different decision rules to understand, what could be driving the behavior of subjects in these experiments. So I'm done with the with the talk, and I'm sort of happy to take questions.
Perfect. Thank you so much. This was a wonderful talk. So if anybody from the audience has any question, feel free to unmute yourself and ask if you want. Maybe in the meantime, I have maybe a more high level question, because I think this platform that you described, it's really interesting, and there's not so many work that are actually really testing with experiments theory of network games. So I was wondering whether you can tell us a little bit more, what are the basically flexibility of this platform to implement maybe other type of network game, or how, if I guess you mentioned if somebody is interested. So maybe if you can comment a little bit more, if any network is available or things like that.
Yeah. So one of the things that's important, I think, is that these experiments, of course, could be done in discrete time, obviously. The more substantively, I think I should mention that we've also run experiments where the linking is bilateral, it's two-sided. So we have to agree to form a link. The experiment I presented today is very simple. I can just decide to form a link with you, and I can go ahead unilaterally. Now, this is reasonable in some games, and some models are like that, but I would say the majority of network models have two-sided, like Facebook. I can't become a friend with you unless you agree. So in another experiment we've run, we've also done two-sided linking, which poses a number of challenges. And what I can say is that the results were actually strikingly clear, even though the problem is. So let me maybe I'll leave it at that. I'm happy to elaborate, but yeah, we have that feature, of the. Yeah, so as you can see in this experiment, there was activity and linking. They were co-evolving. That's the other feature of the platform. You can have both things going on.
May I?
Sure.
Sanjeev. So I just wanted to ask about, so the model was static and your experiment was dynamic. Has a dynamic theory been provided? Are there links to the literature that you'd like to advertise that we can, as a card-carrying theorist, it looks like?
Yeah, so I should say that we don't actually have, so I didn't get into the details, but we can say a number of things about the behavior in the sense that, there's no way that this could be justified in an equilibrium of the dynamic game, because if you think about it, you can see that you should never somehow, there's you can guarantee yourself a certain payoff in the dynamic game. You can just guarantee yourself, you just ignore the rest of the world and you just choose 9, and you're guaranteeing yourself 81. So you should never earn less than 81 in an equilibrium of the dynamic game, okay, in expected terms. But of course, in this particular experiment, it's very easy to see that these guys are earning much less than 81. So that's a simple high-level observation that it could not be rationalized within but having said that, we have not actually solved for a dynamic game, equilibrium of a dynamic game. And more generally, dynamic games of network formation are, I think I can't actually think of a standard model of, dynamic network formation. There are also actually very few games of sequential network formation. they're typically static, or they are essentially non-strategic. So it's very much an open field, I would say.
Let me ask a question again, as somewhat a higher level question. Multi-layer networks. Can you see any extension of this? For example, individuals forming networks on different issues, the same individuals. So there is some correlation between the networks, but there are multi-layers. Any way this framework could be extended to that case?
So again, it's another field where I know there's a lot of interest in multi-layer networks in physics, in the engineering community, probably in computer science. But there is, again, I mean, there's some work in economics, but very little multi-layer games and networks, but also multi-layer network formation. I think there are some attempts, but so we are very far, I think, from doing experiments, because I don't think there is a, if you like, a canonical model of multi-layer networks or games on multi-layer networks. So I think economics is sort of lagging behind, I think, some of the other.
Yeah, the engineering and computer science, several models, and also theoretical sort of computation of equilibrium and so on.
Yeah, I think it's I mean, in principle, there's nothing to prevent running experiments on those kinds of models with this platform. There's nothing, we can easily accommodate that. But just the theory is not very well developed. At least the economic theory is not very well developed. I mean, I think there are very simple ideas you could have that if activities across layers are complements or substitutes, then you can use those high-level ideas to say some things about activity in one network, how it's going to impact activity in another network. And there are attempts at working with those sort of models. But again, I haven't seen, I can't straight away think of a kind of a nice natural model.
Okay, thanks.
Perfect. Is there any other question from the audience? And maybe I have another question, sorry. This was a very interesting talk, I have many questions. So I was thinking, like, here in your payoff, you did the 1 and 2 hope. I was wondering, like, what is your sensing that, like, first of all, do people in their behavior really realize the contribution of the second hope? And if that's the case, would it make sense to extend beyond, like do kind of some Bonnet centrality that kind of accounts like for, like you go beyond 2 hopes, basically. I was like always been curious to understand whether people really can internalize this fact that it's not just the first level of neighbors, but more that do you see some support of evidence from your experiment that they are actually thinking about that?
Well, I mean, the fact that they're doing this pure connector is already suggesting that, that they are realizing that they could be taking advantage of people who are distance 2 away. But you're right. I mean, more generally, one could have, a decay model and do network formation. We didn't do that because we thought it would be, in fact, we thought even this 2-level thing would be very hard for players. We didn't think they would be able to handle it. So I think in retrospect, we think it would have been better to do just the 1 link because that's, I think, much more tractable. But we thought it would be a little more interesting to do the 2-layer, two distance travel. I should say, by the way, that I have another paper which does have linking, which is a standard decay problem. So where you get delta from your first neighbor, delta square, et cetera, et cetera. And there actually, I mean, I might in fact be able to show you some animations of that. There actually subjects are able to figure things out, and they get basically very close to an equilibrium prediction, which is also a hub-spoke network. So they're able to work it out pretty well, even in large groups, actually.
That's
okay,
perfect.
so
That's like when you show them the payoffs, or even if you just like of others, or even in the simple setting.
So, that's a setting. I think that's a setting where we show them payoffs of everyone.
Mm-hmm.
Okay.
That's super interesting. Okay, so I guess if there's no other question from the audience, I guess we can thank again our speaker for this talk, and thank you everybody from the audience for attending.
Thanks very much, Francesca. Yeah, thanks.